Given two functions f and g, in addition to the four algebraic operations, there is another way to construct a new function. It is the composition denoted by a circle. The composition of f and g can be obtained as follows. The value x is used as input for the internal function g. The output g of x is used as input for the second function f, which is the external function. In this way, we obtain the value of the composition as f of g of x. It is worth remembering that the composition of two functions depends on the order in which we use them. So in general, f composed by g is different from g composed by f. For example, using these two functions as ingredients, the function f of g is the sine of 2x minus 3, while g of f is 2 times the sine of x minus 3. Let us now see the result that guarantees the differentiability of the composition and allows us to calculate its derivative using the derivatives of f and g. Let g be differentiable at x and f differentiable at g of x. Then the function f of g is differentiable at x, and its derivative is given by the formula f prime of g of x times g prime of x. That is, the derivative of the composition is obtained by multiplying the derivative of g at x and the derivative of f, which, however, is calculated at g of x. This formula is known as the chain rule. For example, let's calculate the derivative of sine of 2x minus 3 with the chain rule. The internal function is 2x minus 3, while the external function is the function sine. The derivative is the product of the derivative of the external function calculated at 2x minus 3, that is cosine of 2x minus 3, by the derivative of the internal function, which is just 2. We conclude that the derivative is 2 times the cosine of 2x minus 3. Let's see another example.
Let's compute the derivative of this function. It's useful to unfold the composition chain. Let's start from x. G is the inner function that brings x to 3x minus x squared, and f is the outer function that is the power 5 of the inner function. The derivative of y prime, is obtained by multiplying g prime of x times the derivative of f evaluated at g, namely 5 times g of x to the power of 4. Let's now compute g prime, that is the derivative of 3x minus the derivative of x squared, namely 3 minus 2x. Finally, we write 3x minus x squared multiplied by 5 to the power of 4. This is the derivative y prime.
But why is the chain rule valid? We can get an idea in this way. We call big F the composition f of g, that is the function constructed by first applying g and then f, and we fix x. The derivative of big F at x is the limit for delta x approaching 0 of the difference quotient of big F at x, when the limit exists. The goal now is to understand how a change in x propagates up to the external function. We therefore set a small increment delta x equal to h and calculate big F of x plus h following the chain. We call k the variation delta g of the internal function, that is, k equal to g of x plus h minus g of x. The input in the external function f is g of x plus h, which we can rewrite in terms of g of x as g of x plus k. We thus find f of g of x plus k, which is the value of big F at x plus h. We can now write the variation of big F in terms of f and g, and the difference quotient of big F is given by this expression. Now suppose k to be different from 0, so we can divide by k and rewrite the difference quotient as the product of two contributions. Remembering that k is delta g, we recognize in the second factor the difference quotient of g at x, and in the first the difference quotient of f calculated fg of x. When delta x tends to 0, also k tends to 0. Thus, while the second term tends to g prime of x, the first tends to the derivative of f calculated at g of x. This is where the product that appears in the chain rule comes from.